Okay, so like I said, for problem 2, let's fill in the margins. Okay, so we've got 13 managements, and we got 20 supervisions, and we got 117 productions, and 60 guys and 90 gals. Okay, for a total of 150. Okay, so I'm studying this thing. Okay, so let's do A. Let's start A up here. AI. What's the probability to select the worker is female? So that's 90 over 150. Okay, and II, female or a production worker. So I'm just going to use the classic, probability of A plus probability of B minus probability of A and B. So 90 over 150 plus 117 over 150. Okay, so the probability that someone's production is 117 over 150 minus, and here's the probability that production and female is 72 minus 72 over 150. So whatever that ends up being, I don't know what that ends up being. But anyway, that's okay. So that's how you do II. And then III is female if the person works in production. So, so given that they're in production, what's the probability that they're female? So like this. Okay. And so that's what. So production is the denominator, 117, and the female is 72. Okay. And then IV, a production worker, if the person is female, so this is probability of being female. Given you're female, what's probability of production? So probability female. Now, all of these are like over 150, which they all cancel out. So this would be, given your production, I'm sorry, given your female, so that's going to be 90 and 72. All right. Any questions? These are the ones you don't want to get wrong. Okay? It's just working the margins on your tables. Okay? Figuring out which is the given is always the denominator, right? Okay. B. Do these data suggest that job type is independent of gender? So, does the probability of being female, for instance, equal the probability of being female given that you are a production worker? What a question equals there. Okay? So in other words, does it equal the probability of being female and production over the probability of being in production? Okay? Well, the probability of female is 90 over 150. So the question is, does this equal the probability of being a female in production is 72 over 150. And the probability of being in production is 117 over 150. The 150s cancel each other out. This number here, 72 over 1, which equals 72 over 117, equals 0.615. This is 0.6. 90 over 150 is 0.6. Excuse me. So, this is 0.615. Close enough. Okay, you got to be within 0.02. Remember, it's got to be 0.02 to establish independence. Close enough. Okay, hand grenades, atomic war, and horseshoes. They are job type independent of gender. Now, if you did this with management, you wouldn't get the same results. But management numbers are much smaller, right? So it's not as statistically significant as using production. If you did management and supervision, then your numbers, I think, would be okay. It would show independence. Together, if you did them together. Okay, before we move on, any questions? Yes?
You go over to part 2.
Yeah. You mean B? Okay. So I'm going to review B. Does the data suggest that job type is independent of gender?
Oh, no. Part A.
Oh, II? Okay. Okay. Female or production. So here, I'll put it over here. That's probability of female or production equals the probability of female plus the probability of production minus the probability of female and production. Right? Now that's the general law of addition, and that will be on your cheat sheet. You'll get a cheat sheet like you did last time. And these formulas are on there. What's not on there is the rule for independence. Okay, that's not there. But all these other things are there. Okay? In fact, tomorrow I should bring the cheat sheet along. Okay, so that you can see it. All right, anything else? Yeah. Yeah, well, A and B are independent if the probability of A equals the probability of A given that B has already occurred. Okay? And, of course, the probability of A given B equals the probability of A and B over the probability of B. Yeah? Yeah. You got to be 0.02 or less. Less than or equal to 0.02, either way. Okay? That's our cutoff point, 0.02. That's arbitrary. Okay? We got to draw the line somewhere. It would be unusual that your numbers would be exactly equal. Sampling variability, even for two variables that are completely independent, are unlikely to produce exactly the same percentages of the same probabilities. Anything else? Okay? You can always go back to it. Number 12, child's play. Okay, you got a board game. You throw a spinner, and you roll a die. Okay? And the spinner has, well, let's draw a picture. Let's do the spinner. A is the spinner, so probably for the spinner. I'll draw a quick picture. Okay, so here's the spinner, and half of it is 5, and 1/4 is 5. No, I'm sorry, 1/4 is 10, and 1/4 is 20. Okay, so we're going to make a probability model, and we're going to call it capital S. Okay, and then we're going to have some little probabilities, little s's. So we'll have little s and the probability of little s. Okay, so we have 5, and the probability of 5 is 0.5. And we have 10, and the probability of 10 is 0.25. And the probability of 20 is 0.25. Okay, that's probability model right there. Okay, so this is A. All right, now find the mean and standard deviation. Well, I'm going to use my calculator because I'm feeling super lazy. It's 8 o'clock in the morning. I'm not awake. You're not awake. Let's just use the calculator. Please make sure you bring a calculator, okay? Just because I'm not completely adverse to letting you use somebody else's or whatever, but it's just going to be a real pain because you're going to be doing a lot of little calculator type stuff, okay? So, all right. If you don't have a calculator, take notes. Okay, so let's do this. Stat, edit. In L1, we're going to put the S's. That is the outcomes, 5, 10, 20. Okay, in L2, we're going to put the probabilities of each outcome, 0.5, 0.25, 0.25. Okay, like I said, if you already know this, just move on. You know, keep working. Okay, then we're going to do stat, calc, one variable stats, and we're going to specify L1 and L2. Okay, and we can see the first thing you want to look at, does n equal 1? Yes, it does. Okay, so that's a good, doesn't mean you did everything right necessarily, but it sure, you know, if it wasn't 1, you would know you made a mistake. All right, so B, we can see the standard deviation is, I'm sorry, the mean, the expected value of S is 10, and the standard deviation is 6.12, let's call it 6.124, 6.124. So B, the expected value of capital S is 10, and sigma for capital S is 6.124. Okay? Now, create a probability model for the outcome of the die. Okay, so we're going to have big D, okay, and we're going to have a bunch of little d's. Okay, so we got little d and the probability of little d. And we can get a 0, a 1, a 2, a 3, or a 4. Okay? And what's the probability of getting a 0? Well, there's two sides that have a 0 on it, so that's 2 out of 6, and the rest of these guys are 1 out of 6. Okay, there's your probability model. Any questions? Okay, great. Now, yeah, sure. Yeah.
For entering the calculator, so for L1, you're entering the probability.
No, in L1, my apologies if I misspoke, okay? In L1 goes the S's. In L2 goes the probabilities of S. Okay? So we'll run through it again for the D's. Okay? So, for the D's, I'm going to clear the screen first, and then I'm going to go to Stat, and then Edit, and I'm going to just go up to the top and clear this guy, and arrow over here, and clear this guy. Okay, so I'm going to put the D's, the outcomes of rolling the die, in L1. So 0, 1, 2, 3, 4. Okay. Oops, 34. That's unusual. Okay, 0, 1, 2, 3, 4, double check. Okay, and then put in the probabilities. 2 over 6, 1 over 6, 1 over 6, 1 over 6, 1 over 6. Okay. Stat, calc, one variable stats, L1, comma, L2. By the way, if you ever happen to do this and there's nothing in L2, that is, you're doing something else, you just put in a bunch of values in. If you put L1 and L2, it won't hurt anything. Okay, n equals 1, so that looks good. All right, so the standard deviation is 1 2/3. I'm sorry, the expected value is 1 2/3, and the standard deviation is 1.49. Okay, so we go back to here. So D, the expected value of capital D is 1 2/3, and the sigma of D, the standard deviation of D, is 1.49. Okay, so there's D. Now E, find the mean and standard deviation. So E, so what's the expected value? On average, how many spaces do you expect to move? Well, it's going to be S plus D, capital S plus capital D, which equals 10 plus 1 2/3, which is 11 2/3. And then sigma for S plus D is going to equal the square root of 1.49 squared plus 6.124 squared, which is, I don't know what the heck that is. It's something, I don't know what it is. 6.3. Okay? All right? Good? Okay. Beanstalks. Okay, they start out and they give us the mean and standard deviation for the heights of men and women, which are normally distributed. Now, that's a safe bet. Height is something that's going to be normally distributed. It's not a very significant statistic. Generally, the stuff that can be described with a normal statistic is extremely unimportant. Okay, and it's definitely height is one of them. Although height's one of those weird things. It correlates highly to success in business or whatever, and but nobody can understand why. Anyway, okay, so here's men. Okay, approximately normal. I want you to write it just like that. AP, italic N. Okay, and men are 69.1 is the mean, and a standard deviation of 2.8, and women approximately normal with a mean of 64 and a standard deviation of 2.5. Now I'm writing these down just for the sake of reference, okay? And so we're acknowledging it. And this is my way of saying, and for the possibly brain dead person who's grading my paper, that, okay, I know that it's normal. Now you know that I know that it's normal. Okay, so don't give me any baloney about that I didn't recognize that it's normal. Okay, so what does the greater standard deviation for men's heights indicate? So A, men's heights have more variability. It's a very obvious answer, but you got to get that in there, variability. Okay? They vary more, so they have a bigger standard deviation. Okay? All right. B, are men or women more likely to qualify for the beanstalk? Okay. You don't have to do this. I'm going to make a little picture for women. And women, the mean is 64. Now, to qualify for the beanstalk, they've got to be 5'10", which is 70 inches. Okay? So, here's where they qualify for the beanstalk. So what's the z-score of qualification for the beanstalk? Well, the z is going to equal 70 minus 64 divided by 2.5, which is 2.4. Pardon me. Now, for men are 69.1 in the middle, and they need to be 76. How tall do they have to be? Men have to be over 6'2", so 74. Right? 6'12" or 72 plus 2 is 74. Okay, so it's so for men, it's 74 minus 69.1 divided by 2.8, which is 1.75. So it's easier for a man to get into this because he needs fewer standard deviations in order to get into the thing. Did everybody see that? Lower z-score means it's easier to hit the mark. Okay? Which seems strange. If you were, you'd want equal numbers of men and women, you'd think, but I don't know. Okay. So, C. Beanstalk members believe that height is an important factor when people... See, all right, why don't you get the same number of men and women in your... I mean, that seems really stupid. Okay? Isn't there... None of you guys are statisticians? To investigate, we selected random a married man and independently married woman, defined two random variables, and used them to express how many inches taller a man is than a woman. Well, I think M minus W is a fairly adequate answer for C. Okay, M minus W, right? You can use X minus Y, okay? Although I would do Y minus X. All right. And then D, okay, what's the mean of this difference? Well, that's going to be the expected. M minus W is going to equal 69.1 minus 64, which is 5.1. And E, standard deviation, sigma of M minus W is going to equal the square root of 2.4 squared plus 2.8 squared, which is approximately equal to 3.75. How's our room looking? Okay, that's where we're at here. Okay, F, what's the probability a man is taller than a woman? Okay, so now we have a mean and standard deviation for the difference of men and women. And then here in the middle is 5.1. And the difference here is 0. That's always our... Okay, we want to know men taller than women. So this is man M minus F distribution. Okay, so we want to know the shade to the right. Okay, men taller than women, right? So that's going to be everything to the right of 0. So Z equals 0 minus 5.1 divided by 3.75, which is approximately equal to, where is it? I got it here somewhere. Negative 1.36. The probability that Z equals negative 1.36 is approximately equal to, see, I did this wrong the first time, 1 minus 0.087. I'm going to do it on the calculator. I should have written it down. All right, so it's going to be second VARS, normal CDF 2, and negative 1.36. Now we're going from negative, here's negative 1.36. We're going from, that's a Z-score, all the way to a 99. We're going to go all the way to the right-hand tail, 99 Z's. Okay, comma, 99, enter. So, 0.913. Okay? All right. So the probability of a man taller than a woman, in general, okay, to a randomly selected man, a randomly selected woman, probability of a man's taller is 0.913. Okay. Now, all of this super boring, very, kind of straightforward. Finally, you're being asked a statistical question. Okay? Suppose a survey of married couples reveals that 90% of the husbands are taller than their wives. Based on your answer to part F, which means randomly selected man and woman, the man is taller 0.913, or in other words, 91.3% of the time. Do you believe that people choose spouses independent of height? Yes or no? Okay? What do you guys say? John?
I believe that yes, they do choose it independent of height.
Okay. Come on up here. I want you to say it into the microphone because they can't hear you from back here. For whoever's going to be listening to this. Okay? Come on. Okay, we haven't got all day. All right? Yes, it is, but it's broken, but I fixed it with electricals. Okay? Nice and loud, John.
It is independent because the probability of a man randomly being taller than a woman is approximately equal to the probability that a man who is married to a woman is taller than a woman.
Okay. Everybody got that? Okay. Does that make sense? All right. He's completely right. Okay? Now, if height was a factor, in other words, every woman wanted to marry a man who was taller than her, and every man wanted to marry a woman who was shorter than him, then what would you expect? Would you expect this percentage, the 92%, how would you expect it to change? Would it go up or down? Assuming there's a bias. Would it go up or down? It would go up, right? There'd be a bias, so you expect it to be higher than 92%. It wouldn't be the same as the random distribution. Okay? All right. Moving on. Any questions about any of this rigmarole here? Okay? All right. Let's keep going. That's it for the beanstalk. That's it for page 1. Technology on campus. Okay, this kind of gets back to the beginning of the chapter. All right, so the first thing you want to do here is draw yourself a Venn diagram. Now, in a free response question, you're not going to have to do this, but I'm going to want you to provide statistical justification for your answers, and a Venn diagram is an easy way to do that. All right, so here's graphing calculator probability that somebody's had to use a graphing calculator, and here's probability that they have a computer assignment. Okay, now we're told 51% graphing calculator, 31% computers, and 16% at both. Okay, so the first thing you want to put in is the 0.16. Put in the middle. And then what's going to go here in this crescent-shaped space here is going to be 0.51 minus 0.16, which is 0.35. And what's going to go in over here is going to be 0.31 minus 0.16, which is 0.15. Okay? So over here is the people that are taking graphing calculators but not computers. Here's computers but not graphing calculators. There's people doing both, et cetera, et cetera. Okay. What percent used neither? Okay, so A. So neither is all the space outside the two circles. Okay? Now, you got three numbers here that comprise the total area of the two circles. So one way to do this is just simply to say, without using symbols or anything, 1 minus 0.35 plus 0.16 plus 0.15. Okay? You guys follow that? Does that make sense? Okay? Now I can write out all these symbols and everything. Probably you're not going to remember them. It's not a gobbledygook. You don't have to really do it. Okay? But I want you to understand what's going on conceptually here. Neither means the area outside the two circles of the graphing calculator and the computer. Okay? And this is going to be 0.34. So 0.34. So the whole, now we call this is the probability of graphing, probability of calculator. This is 1 minus the probability of G or C. So in other words, these three numbers added together is 0.51 plus 0.31 minus 0.16, right? Okay? All right. B, what percent use calculators but not computers? You can get this right off the screen. Okay. Do I want to disable? What the hell? Jesus. Don't you know I'm using the tablet? What's going on? Okay. So graphing calculators but not computers. Right here. It's 0.35. Can you see it? Okay, this is G and S. Okay, so this is the probability of G minus the probability of G and S. Okay, yes?
Part A doesn't say.
It says what percent use neither kind? Okay?
Yeah, but do you subtract? I don't understand why you subtract 16 because it doesn't say like.
I'm not subtracting 16.
Well,
No. We got three parts, 0.35, 0.16, and 0.15, right?
but you would get the same answer if you did 1 minus 0.35 minus.
I'm doing 1 minus all of this. I'm sorry, I forgot to put in the minus. It's 1 minus those three things.
Since it's not saying like they're exclusively, you're not saying like 31% are exclusively taking computer classes, 51% are taking.
No, it doesn't say that. It says 51% use a graphing calculator, 31% use computers, and 16% are doing both.
But isn't part of that 16% like accounted for by the 31% and 51%? No.
Yes, it's actually in both of them, right?
Yeah.
Okay, which is why if you're going to do G or C, you want to count it at least once. You're not going to subtract it twice. It's in there twice.
Yeah.
Okay? Are you okay? Are you understanding this?
Yeah.
The thing is, if you look at the Venn diagram, the whole square is 1.
Yeah.
Okay? If just look at the three pieces, 0.35, 0.16, and 0.15. These three pieces are the people who are using one or the other. Total. Okay? Don't worry about overlap with these three pieces. Why? Because nowhere here is written 0.51 or 0.31. Okay? This number here is the probability using a graphing calculator and not a computer. Okay? This is the probability using both. Okay? All right? Okay. B. What percent use calculators but not computers? Okay, so it's right there. It's 0.35. Okay, C. This is why the Venn diagram is valuable, because it can really answer the questions for you. What percent of the computer users, of the calculator computer users, had computer assignments? Okay? So, now, this is a little deceiving. This is the probability that given that you are a graphing calculator user, what's the probability you had a computer assignment? Okay, so that's going to be the probability of C and G divided by the probability of G. All right? So that's 0.16, that's 0.16 over 0.51. Okay? All right. D. Based on the survey, the calculator and computer usage appear to be independent. Okay? Does the probability of having a graphing calculator equal the probability that you have a graphing calculator given that you have a computer assignment? So in other words, does the probability of G and C divided by the probability of C to equal the probability of G? So let's figure that out. Probability of that use a graphic calculator is 0.51, and probability of G and C, does this equal 0.16, and the probability that you have a computer assignment is 0.31, okay? And these are close enough. 0.16 divided by 0.31 is 0.516, okay? Close enough for independence. Okay? Everybody all right? Okay, last problem. Coins. All right. Now, so we're going to have a random variable here. We're going to call it capital H. Okay? Now, let's think about it from the point of view of one coin toss. Okay? All right? So we have H, little h, and the probability of little h. So what are we going to have for one coin toss? You can get 0 heads, you can get 1 head. What's the probability of 0 heads? 0.5. Probability 1 head, 0.5. So, what is the expected value of H for one coin toss? Okay, it's half a head, right? 0.5. Okay. Now, the standard deviation for this, you know, by the time I was working on this, I was like not really feeling like I wanted to sit down and do this. I actually did it with the calculator, and I'm a little ashamed of that. But on the list of things that I'm ashamed of, it's pretty low on the list. So, anyhow, what I'm going to put, in case you're in the test and you're thinking, oh man, I can't figure that out, let's put in the probability 0, 1, and 0.5, and let's run the stat and the edit. Oh, what am I doing? Stat, calc, one variable stats, L1, comma, okay. And the standard deviation was 0.5. Okay, now I'm sure I could have figured that out. I'm sure one of you have already figured it out. But anyway, so this is for one coin toss. The mean, the expected value is 0.5, so this is going to help me. All right. Now, I'm tossing it 36 times. So what's the expected value for 36 heads? It's going to equal 36 times 0.5, which is going to be 18. All right, no mystery there. What's the standard deviation for 36 heads? It's going to equal the square root of 0.5 squared times 36, which is going to equal 0.5 times 6, which is going to equal 3. Okay, so the standard deviation is going to be 3. All right, so if we consider two standard deviations to be unusual, so here's 18, and here's one standard deviation, 21, and so 24. So if I get 24 heads or more, that's unusual if I'm tossing it 36 times. If I consider two standard deviations to be unusually high. Okay, you guys with me? What I'm doing here? All right, is this too fast? All right, okay. Now, in 100 tosses, how many extra heads would be We'd say we're unusual. Well, so let's see, what's the expected value for 100 H's? Well, that would be 50, okay? What's the standard deviation going to be? Well, it's going to be the square root of 0.5 squared times 100, which is equal to 0.5 times 10, which is 5. So standard deviation is 5. So I got 50 in the middle. And then one standard deviation is 55, and two standard deviations is 60. So 60 or more heads would be unusual. Okay? All right. So explain how these results refute the law of averages, but confirm the law of large numbers. Let's talk about the law of large numbers first. What statistical change? Now, there's one statistic that changed exactly in a linear fashion, and that's the expected outcome, right? That's simply 0.5 times however many times you toss the coins, right? But the other statistic that we measured did not change in a linear fashion. How is it changing? What kind of change? Remember how we described it? Yeah, Jay?
It doesn't have like a square root function.
Just square root, okay? So if this is like the number of heads, okay, then the square root's going to go on something like that, okay? So what does that mean in terms of the law of large numbers? What does the law of large numbers state? This is something, let's just, what does the law of large numbers state? Who can put it in their own words? It's really common sense. Jay, let's hear it. You got your hand up. What do you think it is?
Well, I was just thinking that does the square root function like approach some asymptote that would be perfect?
No, actually, square root does not approach an asymptote. A square root, the range for a square root function, no matter what it is all reals greater than whatever the origin of the square root is. In this case, it would be all reals greater than 0.
Oh, okay.
So it's going to grow forever, but
Is that slow?
but its relationship to the growth of your expected outcome, the distance between them is increasing, right? Your expected number of heads is going to be increasing, whereas the variation, what's happening to the variation in relation to your expected outcomes? Is the variation getting bigger or smaller in relationship to your expected outcomes? When we did 36, our expected outcomes were 18. Okay? What was the variation? The variation was 3. Okay? Now when we tossed it 100 times, our expected outcome, so let's see, that's a ratio of 12 to 1. Okay? Standard deviation is 3. Now, when we expected 18, okay? We tossed it 36 times. We expected 18 heads, okay? And the ratio of the expected outcome to the standard deviation was 18 to 3, 6 to 1, okay? Now, when we toss it 100 times, how many heads do we expect mathematically? 50, right? What's the standard deviation? 5. What's the ratio of the expected outcomes to the standard deviation? Okay, it's 10 to 1. It's 50 to 5, right? So as the ratio, as the number of tosses gets bigger, what happens to the ratio of the variance to the expected outcomes? That ratio is getting what? Well, the denominator is getting bigger, right? Okay. All right. So that means the variance is going down. Does that make sense? Because it makes sense, right? If you toss it once, you can get 0 heads, and so that you get You know, if the difference is 0 or 100%, toss it 2 times, you know, you could get 2 heads, you could get no heads, or whatever. And the variance is going to be big, right? When you toss it 1 time, what's the expected number of heads? Half. And what's the variance? Half. Oh, I'm sorry, the standard deviation is half, right? Okay, so in other words, the ratio of the expected outcome to the standard deviation is 1 to 1. The more times you toss it, the smaller the standard deviation is in comparison to your expected outcomes. So what does that mean? That means, I'm going to draw another thing here. As you draw, if you're going to plot, make a picture of the outcomes, the more times you toss it, let's say this is 36 is going to look like this, 100 is going to look like this. Why? Because the standard deviation in relationship to the outcomes is smaller. It's getting tighter. Okay? All right, there's less variance. That's the law of large numbers. As the number of trials increases, your experimental outcome, that is what you're actually doing, gets closer to the theoretical outcome, the expected mathematical outcome. So if you toss it 10 times, you don't expect necessarily to get 5 heads. If you toss it 5,000 times, you're going to expect to be pretty close to be 2,500 within a few. You don't expect exactly 25 or it's 2,500, but you expect to be fairly close to it. Okay, that's the deal with the law of large numbers. Okay. All right. Did this help a little bit? Okay. So like I said, I got this recorded, and next class, I'm going to, with my other classes now, you guys are at the end of the chain. So I got 2 other stats classes today, and I'm going to record the review for multiple choice. So, and then that'll go up I'll put that up, and this will go up.
Is that like the 80 stats thing for us to put up on homework, right?
I'm sorry?
It's on like the 80 stats link.
Yeah, I'll put it there. Now, got to see this paper here you guys just filled out? Okay? You got all this down here correctly. You can turn it in the day of the test, and I'll give you credit for it. I'll give you a point on your percentage. Not on the raw score, but on the final percentage. Also, you know, there's 2 homework reviews. If you do them, each one that you do correctly, completely, I'll give you a point for that as well. So you can get 3 points on your final percentage score. Okay? All right. You're welcome. See ya. So long.
So do you need to sign this?
I'm sorry. Let's put it back in there, class. There you go.
Thank you.
Yes. So just, you know, take it when you get back. Don't get sick. Okay? Please don't get sick. Do them, you know, and when you get back, so on. And when you get back, I'll give you a test.
Okay.
No sweat.
Just come find you.
When you get back?
Yeah.
Yeah, you're leaving today, right?
We go to school today, then we don't get back till Sunday.
Okay, just get, you know, the main thing is, when you get back, you're going to have to rest. You're going to be, just please don't get sick. Okay? But I'm glad you're going. God bless you. Okay? It's great you're going.